All right, good evening. Welcome back to Intro to Statistics. We are going to continue our discussion on probability, see if we can't get through the rest of, well, another part of chapter 5 here. So, let's see, in Nevada, there's different roulette wheels depending on which country you live in. Okay, I know the American one is the one this is set up with, but I think the one in France doesn't have two green ones. I think they have either one green one or something like that. But this is ours. So we have a Nevada roulette wheel, has 38 pockets. 18 of them are red, 18 of them are black, and 2 of them are green. Each time the wheel is spun, the ball lands in one of the pockets. Each of the pockets is equally likely. It really is equally likely. Okay, the casinos go through a lot of efforts to make sure that it's fair, that there isn't any bias, and if there is, they change either the ball or they change the roulette wheel. Okay, they'll get it sent up for repairs. What is the probability that a ball lands in a green pocket? Well, let's see here. Let's go ahead and go to our, it's over here. Okay, so let's see here. Excuse me, my cat has a lot to say this afternoon. Okay, so the denominator, right, is that there are 38 possible pockets here. Okay, the fact that they could land in a green pocket, there's 2 of those green pockets for that. Okay, now what do they want? They want 4 decimal places. Okay, so what we're going to do is we're going to go to our calculator and we're going to hit 2, okay, divided by 38. Okay, and then it's going to be our probability that it lands in one of the 2 pockets. Okay, we've already counted for the 2 because that's our numerator. Okay, so this was 0.0526. Okay, 0.526. Okay, so that's a probability that this, by the way, this is why when you look at the odds for roulette wheels, it doesn't quite turn out to be what you want because of those green pockets. That's why the casinos make money off of all of this. So this is 0.0526. Okay, so let's go ahead and we'll check that. Okay. If you bet on green every spin, will you lose more than 90% of the time in the long run? And so the idea that it doesn't land on green is 1 minus 0.0526. Okay, so it's 1 minus whatever this is. That's the probability of not green. Okay, so 1 minus the last answer we have, that's what that is. Okay, and that's going to be about 95, 94 and some change. Okay, so we have 94, looks like 94.74. Okay, so 94.74. Okay, so we have okay. So you'll lose more than 90% of the time. Yeah, 94.74 is bigger than 94% is bigger than 90%. So the law of large numbers says that in the long run, the percentage of time you will approach the 94, the percent we just calculated. Okay, so that's going to be our 94.74. Okay, so that was 0.9474. Okay, put the leading 0 in there. The medical people won't get mad at me. Okay, and then we'll go ahead and see that. That's kind of related a little bit to something called gambler's ruin. Okay. Okay. A lot of people play slot machines and they think, I'm due. You're not due. Okay. I'm sorry, you're really not. So if you're playing these games it's because you're due. They were playing into their idea of wanting to do that. What did I not do? Oh, 94.74%. They put the percentage in there. Ah, sneaky little guys there. Okay. So we're going to go ahead and recheck. Okay. So that's a lot happier. They didn't see that. They didn't like the leading 0. Okay. So you'll lose more than 90% of the time because the law of large numbers. Yes. Okay. So we'll go ahead and continue this one. It's Sherry the kitty. He's not really happy about being picked up, but I'll go ahead and pause this so you can see him. Okay, welcome back. I tried to pick him up to show you his, I figured if he's going to make that much noise, he must have something to say and he must want an audience. But it turns out at nearly 20 pounds, he was not interested in being held, and we're not interested in forcing that issue. So we have survey of 32,000 people, asked how much confidence they had in educational institutions. And then results were as follows. Roger answered to 4 decimal places. Okay, so what do they want to know? What is the probability that the sample person either had a great deal or hardly any confidence whatsoever? Okay, so we're going to add those two together. So a great deal, that was going to be what we have here. We have, there we go, 10,035, 10,035, or, okay, plus, or means plus in statistics, okay? So, or hardly any confidence. There's another rule that talks about if there's some overlap, but we're going to say either it's a great deal or hardly any. So we're going to say 4,249. And then we performed the same number of experiments both times. So we still have a common denominator. So 32,125, 32,125. We could add these together, right? Because they already come with a common denominator. We could just add them up and then figure out what that's going to be. So we could say this is clever and say they have 10,035, okay, plus 4249. So we had a total of 14,284, all divided by 32,125. Okay, that's this one or that one. Okay, which category is it? It's a great deal or hardly any confidence. Okay, so that's what we have for that one. And we'll just go ahead and calculate that to 4 decimal places, because that's what they've said that they wanted to see. Okay, somewhere in here, that's what they said. Round your edge to 4 decimal places as necessary. So we have clear 14,284, all divided by 32,125. 125. Okay. And then 4 decimal places, 444. There's a 6 here, but I wouldn't go with more because they said 4 decimal places, so I would stop at this point. Okay, so 1, 2, 3, 4. 1, 2, 3, 4 decimal places, so 4446. Okay, so we're going to have 0.4446. Okay, and that is our idea there. Okay, check that. Yay, we get the green dot. Let's go on. Okay, what am I on here? I'm on number 8. All right. So let's see here. What is the probability that the sample person had a great deal or hardly any confidence? We did that one. Okay, assume that we have a simple random sample of the population using empirical method to estimate the probability that a person has a great deal of confidence in an educational institution. So we will go back up here and we say, okay, what is a great deal? So we'll just go ahead and calculate that. So that's going to be 10,035. 10,035 divided by the 32,125. When people put the and in, if I said 32,000 and 125, that would mean the decimal point goes where I said the and. So I try to be proper as far as that goes, but Use of English is going to do that. But that's what we're supposed to do. Okay. So Sister Mary Agony could be happy that I've learned at least one thing from her lessons. Okay. And that's how to say numbers. Okay, so we have 10,035. So 10,035 divided by the total number of experiments we did, 32,125. Okay. And to 4 decimal places, 31. It looks like 3124 is going to be the thing here. So this is going to be 0.3124. Okay. So we'll go ahead and we'll say 0 point, and we'll say 3124. 3124. Okay. So just let's do that. 17. Okay. Let's go with that. Okay, we got the little green check mark, so hooray, we're happy. Everybody's happy. If we use a cutoff of 0.05, and this is very common for when we say, is it an unusual observation? In academia, 0.05 is pretty much the cutoff for unusual. And the person who came up with this was the person who came up with a lot of the statistics we use. His name is Fisher. Okay, and he decided that 0.05 is the cutoff. He's like, why did he decide that? He thought it was a nice round number that was easy, because he was one of the great people for statistics. Nobody bothered arguing with him. So he's also not a very nice person, but nobody ever argued with him. So 0.05 is the way that that we just did everything. Okay, so based off the 0.05 cutoff, it is not unusual. We have some confidence. What is some confidence going to go with? Some confidence is going to, oh, did we just do the some confidence? We want some confidence. So that's going to be 17,841. So we want 17,841 divided by 32,125 equals, we'll just calculate this out. So 17,841, 17,000. That's not going to be the good answer. 17,841 divided by 32,125. Okay, so we got 0.5554 to 4 decimal places. So this is 0.1234. Okay, this is like 55 cents versus a nickel. Okay, 0.05. Think of 0.05 as a nickel. Okay. So if it has a cutoff of 0.05, it would not be unusual for somebody to have some confidence. Okay, not be unusual. So if it's unusual, it's going to fall below 0.05. Okay, and again, they chose that because the person who came up with this said 0.05 sounds good to me, and nobody had the wherewithal to argue with them. Okay, so that's how we go. So we can go on to the next one. These aren't too bad. Okay. So we have a survey of 46,122 women. They were asked how many children they had, and they gave us the results as follows. I think I've actually asked this one on a quiz before, so if you're looking forward, like through chapter 5, deciding like which ones could he possibly ask, I have asked this one before. Okay, I think I've asked the roulette one before too. I like the roulette one. I like this one. What is the probability that a woman has had 5? What is the probability that a sample woman has had 5 children? So in this case, we only want the 5. Okay, we only want that category that says 5. Seems like a lot of kids, but 1,016. Okay, I'm not going to judge. I don't know anything. 46,122. So that's our probability that a woman has had 5 children. Okay. There we go. Okay, so we want probability of 5. Let's go ahead and go to our calculators. They're just going to type that in. So we have 1,016 divided by, and our total was 46,122. 122. Okay, hit enter. And then I think they're going to say to 4 decimals, go figure. Okay. We're just going to say 0.0393, but this 7 is going to raise that 3 up to a 4. So we're going to say 0.0394. Okay, so 0.00.0394. Okay, we'll check that, make sure we've done that correctly. Yay, green dot, so we're okay. What is the probability that they had more than 3 children? Okay, so what's more than 3? Okay, so she could have had more than 3. That would be 4 children, 5 children, 6 children, or what do they go up to? 8 or more. Okay, so 7, 8 or more. Okay, so all I'm going to do is just add up all these categories of, what is it, 3 or more? More than 3. More than 3 children. So I'm just going to add up 4, 5, 6, 7, etc. Okay, and then we're just going to go that. So that's going to be 3, 7, 7, 9. That's 4 children plus 1, 8, 1, 6 plus 9, 2, 2 plus 526 plus 773 and hit enter. And then that would be a total of 7,816 women have had 4 or more children. That's what we're asking for, right? More than 3. So more than 3 would be, is 3 more than 3? I think we're going up to, I think when we have that, we have 4 or more is the other way to say that. Actually, that's the hardest part of this class at this point is the English, because the math is pretty nice. The math is pretty straightforward, but the English is the part that's going to kill us all. It's 46, 122. And go ahead and hit enter. So that's going to be 16. This 6 looks like it's going to bring that 4 up to a 5. So I like 1695. Okay, so I'm going to say 0.1695. Okay, we'll check that. Hooray. And then go on to the next little part here. So part C, assume this is a simple random sample of U.S. women using empirical method to estimate the probability that a woman has more than 5 children. Okay, what's more than 5? Well, 6, 7, or 8 or more. Okay, so we're going to pick 6, 7, or 8 or more because they said more than 5. Okay, so I want 922. I want the 526. Okay, we want 773. Okay, we're just going to add those up and divide that by our total. That's how we're going to get this number. Okay, so let's see here. We have, again, let's double check this. They said more than 5. More than 5 would be 6. So that's going to be 922. 922 plus 526 plus 773. Exact total, and then we're going to divide this. Oops, not minus. We're going to divide this. There we go. By 46,122. Okay, hit enter, and then to 4 decimal places because that's what they always are going to ask. More than 5, that would have been 6, 7, 8 or more. Okay, that's what we added up. Boom, boom, boom. There we go. Let's go ahead and type this in. So that's 0.048. I'm going to say that 5 is going to raise this 1 to a 2 because we're going to round. Okay. So we're going to say, if we put this in the right spot here, right, that would be helpful. So we're going to have 0.0482. Okay, so that's our probability there. Okay. I don't want to skip. Oh, check. That's what I want to do. Okay, it looks like we got a green dot, so that's always nice. And then using a cutoff of 0.05, is it unusual for a woman to have no children? Well, how many times do we have 0? Okay, that would be the 15,520. Okay, so would it be unusual for a woman to have no children? We're going to take our 15,000. Oh no, we're going to say 15,520 and divided by, right, 15,520 divided by, okay, 46, 122. Okay, and all we're looking at is it below 0.05. It's about, looks like 33%, right? 33.65%, 0.3365. So that would not be unusual for a woman to have no children. Again, I'm not making a judgment. I don't know anything. So it's just not less than 5%. Okay, that's the only judgment I'm making. Is it bigger or smaller than 0.05? Oops, please be careful. It is not unusual. Okay, how about we do that? So they're happy with that. So I'm going to go ahead and stop our video so it doesn't go on and on and on into the night and start the next one. So thank you for tagging along with the ride, and we'll see if we can't finish up chapter 5 in the next one. Thank you.